Hello, it's Keith here, and this is lesson 74 of the platform-specific series of my Z80 assembly programming tutorials. We're back on the Sam Coupe, and we're back doing sound again. Why are we doing sound a second time? Well, last time we made ChibiSound, a little simple sound driver for simple bleeps. This time we're making the slightly improved ChibiSound Pro for making slightly better bleeps, but also for doing simple music. I've written a music player called ChibiTracks, which is a multi-platform, multi-CPU music player that can play the same sound file on lots of different systems. How does it do this? Well, ChibiTracks is a different copy of the program for the different CPUs, and then it passes its sound commands to ChibiSound Pro, which is the platform-specific sound driver. It's essentially a hardware abstraction layer which takes the requested data commands and works out how to do it on the underlying hardware. Now, these commands take the form of 4 bytes. The H byte, the byte in the H register, bits 0 to 6 are the channel number, so 0 to 127 could be passed to us, but we actually only need to process 3 channels really for music. And the top bit is the noise on and off bit. We've then got a 1 byte volume, 0 to 255, with 0 being silent. And we've got a pitch, which is 16 bits in DE, with 0 being the lowest pitch and 65535 being the highest pitch. So those are the parameters we're going to be passed, and we're going to have to work out how to make those work nicely on the Sam Coupe. So how does sound work on the Sam Coupe? Well, it's pretty advanced actually. We can set left and right volume level for our 6 channels. We have pitches for our 6 channels. And we have a noise generator. Now actually ChibiSound Pro requires us to be able to turn noise on or off for each of our channels, and so what we're actually going to do is we're going to do some tricks, and this is a common problem, but the solution I use is, what I do is I keep track of when we're asked to turn the noise on or off for our channels, and I keep these as a sort of virtual noise channel, and then I remap them all to the actual functional channel. And so we're going to reserve one of our channels, our channel 3, as the frequency for the noise, and then we're going to use that frequency as out for our noise generator, and then that will become the noise channel, and then the other 5 channels will be able to do the work. And as I say, ChibiTracks really only wants 3 channels because it's based around the original AY synthesis, so we don't really need more than that. So we've got a variety of settings here that we will need to change. Now, when we want to write a register, a sound register, what we do is we first write the register number to port 511, and then we write the new value for that register to port 255. Okay, well, let's go over to our source code and let's see, and also hear the thing in action. So we've got a couple of things we're going to have a go with today. We've got the Chibi Tracker test, which is the music test, the ChibiSound Pro test, which is the debugging tool, and it's actually Sam V1 ChibiSound Pro, which is the ChibiSound Pro driver. Okay, let's try this simple one first then. Okay. So here is our value on the screen, and we've got a pitch here that only dogs can hear. Let's turn on our scope here. So there we go. Now if I use the correct keys, you can see as the number goes lower, the pitch is going down. And if I press the control button, I can turn noise on and off here. And you can hear we can change the frequency of our noise as well. So that's just a simple test routine to allow me to basically debug the driver. The more interesting thing, of course, is to be able to play music. So this is the Chibi Tracker. Now this is playing the Chibi Akima's theme. Now the Chibi Akima's theme was originally written in Arcos Tracker, and what I did for my 10K subs is I converted it to my Chibi Tracker Pro and then exported it as a binary file for the Amstrad CPC, and it's the same binary file that's playing here. And that same binary file can be played on the 6502 systems and even the 68000 systems, even though the 68000 is big Indian. So the point is, export your binary once, play it on all the systems. That's what the whole purpose of this is. So there we go. Now the music file won't sound exactly the same on every system because the technical sound on every system isn't the same, but it's intended to sound at least as close as is possible. You know, it's a best effort attempt. Now the frequency values we pass in DE to ChibiSound Pro aren't matched, so the value 32768 will be a middle tone on every system, but it won't be the same middle tone. When we want to actually do notes in an octave, we have a lookup table called Chibi Octave, and we have the 16-bit values to pass in DE to get the various notes, and if we want a sharp or flat, we just take 2. So if we wanted C sharp, we would take the C value and the D value, add them together and divide by 2. Okay, so there we go. Now when we want to actually use ChibiSound Pro, the first thing we need to do is we need to initialize it. So that we would run this routine here. And the first thing this is going to do is it's going to basically initialize the sound register number hexadecimal 16 to this value here. Now hexadecimal 16 is the noise generator, and basically the bits that we set here will define which one of the channels defines the frequency, or we can have a very limited range of fixed frequencies, but we don't want that. So basically we are using frequency generator 0 and we're mapping to channel 3 here, and that's what this combination of bits are doing here. That's the 3-3 part in there. 3-3 is the new setting and 1-6 is the channel number, and we're using set sound register BC to do that. We also use it to turn on our sound with register 1C, and we set that to value 1 there. Now this is the routine I'm using here, and we've got another routine called set sound register which we'll also use later. And so basically to select a register we set BC to 511, and then we write the value of the register we want to select to that port, and then we write the value of the new value of the register to port 255. So 511, if we decrease the top byte of that, we end up with 255. So we're writing that to that second port there. So we can use set sound register to set a register, or set sound register BC, depending on what we want to do. Now we're going to need to do some trickery, because we're going to use that channel 3 for all of our noise. So whatever we were asked to do our noise on, if we were asked to do it on channel 0, for example, we're going to redirect it to channel 3. So we could be given any numbered channel to play to from 0 to 127. So we're going to use a map and remap those channel numbers and avoid channel 3. So Chibi uses lower numbers as higher priority. So if we could only play one channel, channel 0 should be the channel to play. So the higher numbered channels become less important. So you can see here we start from 0, 1, 2, 4, 5, 2, 4, 5. So we're repeating those second ones, giving 0 and 1 most priority in there. Now we also have a set of masks. Now these are the bits for the channel numbers. So these are the channel numbers in the 0 to 5 range, and this is for us enabling the various channels, because when we want to enable the frequency or the noise, we need to set one of the 6 bits from 0 to 5 in these entries here, and so these lookup tables are going to mask those bits for us. Now beyond that we do need a couple of other things. Now some of the registers are actually shared, so basically the octave registers use 3 bits for each channel, but there's 2 channels in each of these registers, and so when we write a value to these registers we're going to remember what value we've written, so that if we are changing channel 0's octave we don't want to mess with channel 1, so we're going to keep it to the same, we're going to keep it in that cache. And the same is true for the frequency and the noise enable. So we're going to define some bits of RAM here for the channel enable, for the frequency and noise, and the octave setting. We're also going to define some bits for the virtual noise flags, because as I say, we could be asked to turn noise on any channel. We're going to map it to channel 3, but then later on we might be asked to turn it off again, and we need to remember that it was on before, so that we then turn channel 3's noise off. So you're going to see that in our code as well. Okay, so let's take a look at the actual code that handles this. So we would run ChibiSound Pro set. We'd set H to our volume number, L to our channel, and also the top bit is the noise. There we go, top bit noise, and D is our pitch. So the first thing we're doing is we're getting our L value, and we're keeping the top bit because that's our noise bit, and we're taking the remaining 3 bits, the bottom 3 bits, and we're looking those up in the channel map. So every 8 channels would wrap around. We're then loading in our new channel number, the hardware channel we're using, oring back in that noise bit and storing the converted value in L. Okay, so now what we're going to do is we're going to get the entry within the channel noise setting. So this is the virtual channel state. So we are going to load in our channel number here, and we're going to basically look at the offset for the current channel. We're then going to see if we're now being asked to turn noise on or off, and if it's being turned off, we're going to jump down here. Now if noise is on, what we're going to do is we're going to set that flag in that virtual channel noise, so that we know that the noise was asked to be turned on this virtual channel. We're then going to get the channel mask. Now this get channel mask routine, where is it? This get channel mask will look up the entry within the channel masks for the current channel, and what it will basically do is it will get the correct one of these masks for the current channel, and then it will load DE with the channel cache enable flags, which are the values for the frequency enable and the noise enable, and so there's just 2 bytes of that. So when we use this get channel masks up here, what we are going to want to do is we're going to actually disable the tone channel for the current channel, and so we want to change register 14 here, and we want to disable the current channel. Now this channel disable function, what it will do is it will read in the current value from our channel cache enable. It will then and setting the bit for the current channel to 0. So this is going to silence the channel. These values for B and C were set by get channel mask. It will set B to the bit being 1 for the current channel, and it will set C to the bit being 0 and the other bits being 1 for the current channel. So by ANDing with C, we're setting the current channel's enable bit for the frequency to 0, which silences the channel. We're then writing that back into the cache for next time, and we're then running it through set sound register with the value in the accumulator as the channel number. Now we set that with with register 14 in hexadecimal, so that is frequency enabled. So we've silenced the tone channel. It's because we're going to use the noise channel instead. We're making a shift to the volume. The volume for the noises was too loud, so that's a correction there. And then we're loading L with the value 3 as the channel number, because we want all of our noise to go to the tone generator 3, which is been controlling the noise because of that setting we set before. Now that's what we do if noise is on. If noise is off, we're doing something different. What we're doing is we're checking BC, which is still pointing to the virtual channel state. Now we set that to on when the noise was enabled, but now we're going to see if it's currently still set to 1, because if it is, then this channel was playing noise before and now it isn't. So in that case we set the flag back to 0, but now what we want to do is we want to turn off the noise generator. So what we're going to do is we're going to basically do almost the same thing here. So we're going to run the get channel mask here, and then we're going to run this noise off routine here. Now this noise off routine is a bit special. What it's going to do is it's going to skip to the second byte within the channel enable bytes, because the first one was for register 14 and this is for register 15. And so what this is going to do basically is it's going to disable the noise generator for register 15, and so that's what this is doing here. We're just using this channel disable function again to silence the noise there. So that's turning the noise off because we know from that flag there that it was previously on. Okay, well we're now done with that. Now one thing we've got here that we're not going to cover is I did put in some experimental code for envelopes, but that is not supported at this stage, so that's just some test code that I've not taken out. I'm not going to take out code I might want to use later, but it does not work at this time in any reliable way. So the first thing we're going to do here is we're going to set the volume. So basically we've been passed a full byte, but actually we use 4 bits for left and right volume, but ChibiSound Pro is actually mono still, because most of the systems, a lot of the systems are still mono, so it didn't seem sensible to go to stereo. So what we're going to do here is we are going to take the top 4 bits in from H. If they're 0, then we're going to silence the current channel by setting the register 14 to silent again. But basically, otherwise, what we're going to do is we're going to double that value up so that we're setting the left and right parts both to the same value here. We're then going to take our channel number and we're going to use that as the register number, because the amplitude generators, the volume generators for channels 0 to 5 are 0 to 5. So we are just sending that and setting our sound. Now the next thing we're going to do is we're going to set our octave and frequency. So basically on the Sam Coupe, this works as a 3-bit octave and an 8-bit frequency. And so what we're going to do is we're basically going to shift our 16-bit value so that we've got 3 bits for our octave there and the remaining 8 bits for our frequency. So we're ditching some of the E bits there just to with some bit shifting. And then what we're going to do is we're going to set our tone generator frequency, that's the low byte effectively, and they start from register 8 onwards. And so we're calculating that here, adding 8, so selecting the correct sound register and setting that. And then what we're going to do next is we are going to basically set the correct part of the correct octave register. So there's two different channels being set in each octave register, and so we're going to need to keep one and change the other. So we've got a mask here to keep one, and what we're going to do here is we're basically going to bit shift. And so what we're going to do is we're going to test bit 0 of our channel number, and if that is a 1, then we're going to need to bit shift everything into the correct position so that we change the second one, because if the bottom bit is 0, we would be changing that bit. But if the bottom bit is 1, we're changing that, that, or that. And so what we're going to do in that case is we're going to shift this mask, and we're going to shift our 3-bit octave number, and we're going to shift those into the correct position. What we're then going to do is we're going to get the entry in the channel cache for the octave registers. We're going to AND it with E, which is the mask to keep the bits of the opposite octave that we don't want to change. We're then going to OR it with D, which is the new value for the octave that we do want to change. So we would be either changing 0 and keeping 1, or changing 1 and keeping 0 if we were changing octave register 10 in hexadecimal there. So that's how we're basically keeping the one value, changing the other, and getting our new value. We're then storing that value for next time, because next time we change this register, we need to keep the other octave the same again. And we're storing our correct value to change. We are then basically dividing the channel number by 2 and adding hexadecimal 10 there. And so that's basically setting 10, 11, or 12 as our destination register, and we're setting the sound. Now, at this point, basically what happens last is going to depend on whether we are making a noise or not. So we're getting the address for our channel mask. We are checking if the top bit of L is 1. If it is, we're going to be making a noise. Otherwise, we're making a tone. So if we're making a tone, basically we want to enable the correct bit for this channel in register 14. Register 14 is the frequency enable. Otherwise, we want to do that for channel 15. And so in either case, what we've got is this channel enable function. What this does is it uses the value that was calculated by the get channel mask in B to set the bit for the current channel to 1 and sends that to the sound register. So that would be for the frequency enable or the noise enable. If we want to disable the noise though, or disable any channel for that matter, what we need to do is we need to mask with C, which has every other bit other than the current channel set to 1, and so that sets the current channel entry in this to 0, and that will turn that off. A little bit complicated, but there you go. So there we go. So that's all we're going to be covering today. The Sam Coupe's sound is pretty good. You know, it's very capable, in fact. You know, there's been a little bit of complexity with regards to how we have to deal with the noise and the shifting the bits around, but you know, nothing too ridiculous. And as I say, a very nice, capable piece of hardware. So I'm very happy with it. Anyway, I hope you've enjoyed what you've seen today. Go to the website, download the source code, the build script. I would say you want to do anything you want with it. You can use this as a template to build your own far better music software. I'm sure you can. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.